Hello and welcome. In this video, we will start introduction on formal languages. There are lots of languages are available for communication like English, Hindi, French, Persian, Urdu, and so many other natural languages. And there exist millions of strings in all those languages, but it is very difficult to interpret such natural languages because of many reasons. Like every language has its own idioms. The meaning of idioms is different than the actual or the dictionary meaning of those statements. Then there are so many slangs, dialects, metaphors, multiple meanings of a same word that makes it very difficult to define a specific rule to understand the language. So we cannot directly adopt that language. Right? It depends on our ability and intelligence to understand the natural language. So as we come across various books, as we communicate with people, as we talk it, as we start using it in our day-to-day life, that vocabulary and understanding increases day by day, and we might learn that what is the meaning of particular idioms, how to use the slangs, what are the dialects, etc. So the scope of natural language is quite big, and it is very difficult to define it within a particular norms. Like all communication language, we have computer languages as well, and we need a specific rules to define such languages. So formal language is fully defined by explicit rules. Like there are certain symbols. Like in English, we have A, B, C, D up to Z. Similarly, in formal languages or computer languages, we have symbols of the languages, okay, that we have to state explicitly that only these many symbols are valid part of language. So that could be either A to small a to Z, capital A to Z, some numbers, okay, might be some operators, special symbols, etc. Through symbols, we can construct the strings. So strings are also defined through rules because any random combination of symbols will not form the strings, right? There must be some specific way to define the strings, like strings of odd length, strings of even length, or maybe strings which are starting with A and ending with B. So there are such rules imposed on such formal languages, and that we need to define explicitly. And rules to form sentences that are also defined explicitly. So once we have some small strings, we can define the rules to construct the statement as well. That there should be first article, then verb, then a noun, and something like that. Okay, so whatever rules we are following in our communication language, that we can explicitly formulate, and that will define our language. So formal language is basically a subset of all the sets of possible strings from set of symbols. So if we have symbols like A to Z, then infinite strings are possible, but they all doesn't make sense. Right? There are a lot of strings which are not useful or they are not making any sense, so they will not be a part of language. So formal language is a subset of set of all possible strings that we can construct from the set of symbols. Example, like the set of all syntactically correct C program that will form the C language. Right? If we are writing wrong program, suppose we are not adding a closing curly bracket or we missed out semicolon, then all those programs will not be the part of C language because they are syntactically incorrect. They are not satisfying the rules of writing the C programs, and hence they are not part of language. So languages are having a strict rule, and every statement must have to satisfy those rules. Then only they can be considered as a part of the language. Let us try to understand the basics of the formal languages. So the symbol is the first and the foremost important thing. Symbols are basic building block of any language. Maybe it's computer language or maybe it's a communication language. For example, in English, small a to C, capital ABC. If we talk about the digit, then there could be 0, 1, 2, 3 up to 9, etc. Special symbols can also be a part of symbol like plus, minus, division, exclamation mark. Alphabet set is a finite set of symbols. So all the languages are defined over finite set. So we have to fix it that what will be the set. Like Sigma, this alphabet set is typically denoted by sigma. Sigma is equal to 0, comma 1. That defines the binary alphabet. If we want to construct the binary language, then we have to use two symbols only, 0, comma 1. So that is the alphabet set for binary language. Similarly, for decimal alphabet or decimal language, we can have sigma is equal to 0 to 9. For lowercase letters, we have sigma is equal to A, B, C, D up to Z. Right? For uppercase letters, we have sigma is equal to capital A, capital B up to capital Z. So according to our requirement, we can define the sigma and we can write down the rules to construct the strings from that. So basically, string is a finite sequence of alphabets. So when we combine these symbols, small a to small z, small capital A to capital Z, or maybe 0, 1, etc. So that combination or concatenation of symbols will form the string. So any string will contain only terminal symbols, or we can say it will only contains the symbols. Okay? So W is equal to ABB, X is equal to 0, 1, 1, 0, 1. So see that on right hand side of both the symbols W and X, it's always coming from the some symbol sigma. So they are called the strings. Empty string is a special string in which there is no symbol involved. Okay? There is no symbol is present. For example, W is equal to epsilon, and epsilon indicates it is a null symbol, or it's a blank. There is no actual symbol is present. That's called empty string. Length of string defines the number of characters present into that string, and it is represented by mode of the string. That is, mode of epsilon is 0 because there is no character is present. Mode of ABC string is 3 because there are 3 symbols are there. So that defines the length of the strings. String concatenation operation. Consider we have two strings, x is equal to AAB and y is equal to BAB. So concatenation of x and y is defined by the dot operator x dot y. But in practice, we normally do not write that dot. Okay? So concatenation says we have to put both the strings side by side. First we have to put x, and that should be followed by y because our concatenation sequence is x dot y. So that would be AAB dot BAB. But as I said that writing dot is not that convenient, so we just ignore that dot. And finally our string would be AA double B AB. And YX would be reverse of that because first now we have to put Y and then we have to write down the X. So that would be BAB and followed by AAB. X into X. It is also known as a X square. So here we are repeating the same string. X is concatenated with X. So that would be AAB followed by AAB. Remember this rule, whenever we concate epsilon with any string, maybe epsilon followed by X or X followed by epsilon, that will give you the X itself because epsilon is not a symbol, it's a null. It means we are not concatenating anything with X. So that will remain the X itself. String reversal. So if our string W is AAB, then its reverse string is denoted by W power R. So that will be the exactly reverse of it. That is BAA. Power of alphabet. So let's see what kind of language we can generate through the alphabet, and that is very important. So normally sigma power k is collection of all the strings of length k. So we will define our language over a certain alphabet. For example, alphabet set is A, B. We have only 2 alphabets in our language, in our alphabet symbol. So sigma power 0 indicates all the strings of length 0. And we know that there is only one string is present, which is having a length 0, that is epsilon. Sigma power 1, it says it's a collection of all the strings of length 1. So we have 2 symbols in our alphabet set, A and B. And we want to generate the strings of length 1 only from using those symbols. So only 2 strings are possible. One is A, another is B. So these are the strings of length 1. Sigma power 2, it means we have to concate sigma with sigma. So it defines all the strings of length 2. So we have first sigma, that is AB, concatenated with the same sigma, that is AB. And now we have to take the combination of all alphabets. So we will get 4 strings. So we have 2 alphabets A, B, and using that we have to construct strings of length 2. So that would be AA, AB, BA or BB. Right? Similarly, if we can go on, we can have a generalized form, and that is known as a clean closure of the language. So clean closure is defined by sigma star, and sigma star says 0 or more occurrence. So that is sigma power 0 union sigma power 1 union sigma power 2 union, and it goes up to infinite length. Okay. So sigma power 0 we have already computed, that is epsilon. Sigma power 1, that is a comma b. Then sigma power 2 would be double A, AB, BA, BB. Then sigma power 3 would be 3A, AAB, ABA, ABB, BAA, etc. And it goes on. So it contains, sigma power always contains all possible strings that we can construct using the alphabets. There is another notation which is called positive closure, and it is defined by sigma plus. So positive closure is just a little bit a modification of clean closure. In clean closure, epsilon is a part of language. In positive closure, epsilon cannot be the part of the language. That's the only difference. Okay? So null string is not allowed in positive closure. Otherwise, everything is same. So sigma plus is written as sigma power 1 union sigma power 2 union, and goes on. So our language would be A, comma B, double A, AB, BA, BB, then triple A, double AB, ABA, and so on. All the possible strings that we can construct using A and B. We can say that positive closure is subset of clean closure, because clean closure has one extra string compared to positive closure, and that is sigma. Or we can write sigma star or clean closure is positive closure union epsilon. So when we add epsilon into the positive closure, we will get the clean closure. And language is set of strings chosen from some sigma star. We know that sigma star indicates all possible strings that we can construct from the given alphabet. So only 2 alphabets are given, but from that we can construct infinite strings as shown in the first line. Right? Strings of length 0, strings of length 1, strings of length 2, strings of length 3, and it goes on. Now language imposes certain restriction on the strings, and only strings which are satisfying those restrictions or the rules, they will be the part of language from the sigma star. Rest we have to reject. For example, L1 is equal to set of all strings of length 2. So sigma star is having infinite string, but from that we are defining certain rule and we are forming the language. So what L1 language says, that it contains set of all the strings of length exactly 2. So now L1 is restricted, and it will have only 4 strings as a double A, AB, BA, and BB, because only 4 strings are satisfying the rules of language L1. So L1 is, or any language, is definitely going to be subset of sigma star. So as we change the rules, our language will keep changing. Let's consider another example, that L2, language L2 is set of all the strings ending with double A. So it can have anything before it, but it should end with double A. So the minimum length string would be double A. Then strings of length 3, that is A double A, B double A. Then there will be strings of length 4, that is double A, AB double A, BA double A, BB double A, and so on. It goes on. Okay. You see, there will be infinite strings, but still L2 is subset of sigma star because it doesn't contain sigma, epsilon, A, B, strings ending with B, strings ending with A. Those strings we have to reject. L3 is set of all the strings which are starting with A and ending with B. So again, it will be a subset of sigma star. We only have to consider the strings from the sigma star which is having initial letter A and last letter B. So minimum possible length string would be A, B. Fine. Then we can have A and B in between that AB. So the strings would be AAB or ABB. Then we can have 2 letters between A and B. So that would be double A, AB, BA, BB. And first letter would be A, last letter would be B. Then we can have strings of length 5 and so on. That process goes on. For example, C language. So for C language, we know that we use various symbols. We use various English letters, small, capital is allowed. We also use numbers for defining the variables or writing the programs. We also use various kind of symbols like plus, minus, parentheses, right, division, curly brackets. So all these will form the sigma for the C language. And there will be certain rules to define the language. Like for example, program P1. That is hash include stdio.h void main. So this is the syntax of basic C program. And if it is syntactically correct, then we can say that this program is part of C language. And when we collect all such infinite programs, program P1, program P2, program P3, all will be the members or the part of C language. So C language is nothing but it's a set of all valid programs P1, P2, P3 and up to P infinite, provided they are syntactically correct. Language concatenation, like a string concatenation, we can also perform the language concatenation. So here instead of combining two strings, we might be combining or concatenating strings of one language to all the strings of other language. So consider L0. So that is called language of strings having length 0. So that is only epsilon. Right? So empty is empty language. So there is a distinction that when we write just a curly bracket, opening and closing brackets, then it is called empty language. There is no string at all. And when we write epsilon within curly bracket, it says that this language contains one string whose length is epsilon. So there is a difference in both of this, mind well. L1 is equal to L, L2 that is L into L, we have to concatenate language with itself. L3 that would be L into L into L. So we are concatenating L with L and then again that we are concatenating the same language again. So it is something like very similar to the string concatenation. Clean closure of language is defined by L star. Okay, that is again L of 0, that is language of string length 0. Union L1, language of string length 1 and so on. Similarly, we have positive closure for the language, that is L plus. So L0 will not be the part of positive closure. Theory of computation, why we need to study this? So that what we have seen was very basic things about strings and symbols or building blocks of the language. But why we need to study this subject, theory of computation? Because it is a branch of computer science that deals with how efficiently problem can be solved on a model of computation using an algorithm. So in upcoming lectures, we are going to discuss various models for accepting the language. Okay? And those languages would be either simple language, or it could be a programming language, or it could be any complex language. Okay? But for everything, we can have a computational model. And actually, we can divide it into three parts: automata, theory and language. So that part deals with definition and properties of various mathematical model of computation. So very soon we are going to discuss finite automata, and that will be followed by push down automata, Turing machine and all. So that branch of this theory of computation deals with defining various mathematical models of computation. Then there is another section called computability theory. So it deals with what can be and what cannot be computed by the model. So model cannot do every kind of computation. Computability theory will says that what kind of problems can be solved and what kind of problems cannot be solved. And finally, there is a complexity theory. So complexity theory basically derives how hard particular problems are, so that we can group the problems with similar complexity together. Why? That these problems can be solved in linear time. These many problems can be solved in logarithmic time. These problems are exponential time problem. So complexity theory allows us to compare problems based on their hardness, or we can say we can categorize the problems according to their computational cost. Right? So that was all about the introduction of the theory of computation. And from upcoming videos, we will start discussion on finite automata. Thank you. That's it for today, folks. See you in next video. If you think this video was useful to you, then please like, comment and share. Don't forget to subscribe the channel CodeCrucks. Press the bell icon for the notification of latest videos. Stay connected, stay tuned. Thanks for watching. Bye-bye.